basics of garbage collection. Or it's a very high level thing. It's just about giving you ideas about where you can look and what garbage collection actually means. A very basic overview. So yeah, so I've called it cleaning the trash in Python. So what is overview? Why?
Hello.
Hello. It's better? So what I'm going to be talking about is basic garbage collection, an overview of garbage collection in Python. So, when you have a big house, if you don't, if you're not much of a big cleaner, maybe you're a bachelor, right? You bring your friends in. Over time, what happens is your house tends to get messy. Now, things, you can't find the things where you want it to be and stuff like that. But now, when it comes to programming languages, what does it actually mean? What does trash mean in a programming language? So, what do you think? What do you guys think? It's kind of basic. Most people should know. What do you think trash, or at least garbage, in a programming language means?
Any data that has been stored which is of
Stale
no
objects.
Objects which are there in memory and which are not being used anymore, right? So that is basically what you mean by garbage in programming languages. So memory. Now everything works with memory, right? When you initialize objects, you need to store it in memory, right? And if you're not going to be using that memory, if you're not going to be deinitializing that object out of the memory, what's going to happen eventually is you're not going to be able to initialize new objects, right? So as the garbage increases, your chances of allocating new memory kind of diminishes. So in order to understand that, we're going to have to talk a little bit about memory. And so there are two basic data structures that I'm going to touch upon, but I think this should be basic. You guys must have heard about it at some point of time. One is stack, one is heap. If you want, I can just rush off. Does anybody need an explanation of what these two basic data structures are? Okay, so I kind of had put in some stuff. When you say push, on a stack, or just to give a basic overview, when you're removing an item from a stack, it's always from the top. The last object that you inserted is the one that's going to be taken out. On a heap, it's basically you're going to ask for a chunk of memory, and the heap is just going to give you that consecutive chunk of memory if it is there. If it's not, like let's say in this particular thing, you want to push DE, even though a heap has 2 memory units left, he will not be able to give it to you because it is not together. Right? So you get something like a heap error. Now there is a difference between how objects are allocated in C and how it's allocated in Python. Now on C it's a very basic stuff, right? C, you compile everything, you know the objects beforehand, and you basically store it on the stack. Now the stack, okay, so before I go into that, the stack is the stack, you basically get a stack overflow error at some point of time, and you guys must have seen it if you're doing a recursive function. When you do a recursive function, you get a stack overflow error. A heap, you usually don't get a heap, you don't run out of memory on heap, because the OS, whenever you need an extra space for heap, you request the OS gives it to you, right? So heap can keep increasing. But how do objects and variables get stored on C? So whenever you run something, like let's say you have something like that in C, int a equal to 5, int b equal to 5, int star c equal to null. For those who don't understand C, what you're doing here is, C is a statically typed language. So when you say int a equal to 5, what you're saying is, I need an object, there is a variable a which has a value 5, and the data type of that 5 is basically an integer, right? So what happens is, let's say this is in the context of the main function. What you're going to be doing is, on the stack you would push the main function. It would have a lot of variables. This is just very simplified. It would have some pointer locations pointing to some. I mean, there are a lot of variables over here. You don't really have to bother about that. But what happens is you have local variables as well. In this, the A, B, C are basically local variables. Now that star implies that it's a pointer, which means it doesn't have a value, it is pointing to a value, right? So it's a dynamic memory. When you say A equal to 5, what you're doing is, this is a binary value of 5. So when you say A equal to 5, you store the value over here. You have the variable name, you have the value, and you have a type. So A is 5 and the type is integer. B is 101 and the type is integer. C is a pointer. Okay, so pointer is different from this value, right? So you basically, in C, how you define a variable is, you have the name, you have a pointer, and you have a value. So when you say A equal to, the pointer C has something, you basically say the variable name is C, the pointer value is this, then it's null, it's basically pointing to nothing, and the value, it doesn't matter, right? Now what happens when you do something like B equal to 6? It basically goes to this variable and it changes this to 6, right? So as you can see, we haven't utilized a heap as of now. When does C utilize heap? When you do something like that. When you do malloc, which is basically asking for a chunk of memory of the size integer. Here it is size of integer, and you're saying, give me a chunk of memory of the size of integer, and he'll basically go ahead and create something over there, and he will return that address. And the next step would be just updating that. Now it is pointing to that, right? So that is how dynamic memories kind of are implemented in C. How does it work on Python? Right? Now when you have something like A equal to 100, what actually happens in Python is, you create an object on the heap, right, which has the value 100. And then there is a variable which is there on the stack, which will basically point to that value. Right? I've done all these animation kind of things. Now what happens when you say something like B equal to 100? Right? Now there is an object with that value 100. It is basically going to reutilize it. So what all that you're going to do is, you're going to create a variable, a name called B, and it's going to point to that 100. Right? It doesn't work the same as how it is done in C. Right? What happens when you do something like this? C equal to 100, 100. Now there are two types of objects. There are two types of objects that you can have on Python. One is simple data, simple objects, which is what you see over there. It's simple. It's either an integer, it is either a string, or it's a float, right? Even a tuple is kind of static, so even that is a simple object. But a list is a dynamic thing. You can basically go in and you can change the value of this, right? So it's kind of static. So what happens in this case is, you basically create a complex data type, which in turn is pointing to some other objects, right? C is basically pointing to that complex data type, and then you're just gonna point to that object, right? And I'll just give you, I'll just show you how you can basically look at it in. Let's say, okay. So I'll just open up Python interpreter here. Now, does anybody know what this ID does? Okay. It gives you the memory location. So now, if I say ID of A is not there. Now, if you do A equal to 100.
In case of font size.
How do I do that?
Properties.
Control plus plus. Command prompt.
So when you do a equal to 100 over here, it's actually pointing to some memory location. Just look at the last 4 digits, 9680, right? Now b equal to 100. By my explanation, it should be the same memory location, right? 9680. So it's basically pointing to the same memory. I'm sorry. Okay? It's basically going to be pointing to that same memory location, right? Okay. What happens if you say a equal to 101? A is now no more going to be pointing to 9680, it's going to be pointing to 9696. Right? Now let's try something else. Let's say this. Okay, this is the other example that I did. So the ID of C is basically going to be some memory type. You guys can't see it at the back, can you? Okay, fine. So basically it is some memory location, but what is ID of C of 0? It's basically going to be pointing to that 9680, right? So objects are static. In Python, objects, when they're created, they're basically static. All the names that you create, like a equal to something, is basically referencing an object which is either there, or if it's not there, it will create it, right? And that's how memory kind of works. Now each object, right, has a structure something like this. What this means is there is a type. Basically what it will tell you what that type is. It's either an integer or it's either a complex object or whatever it is. The value of that, it can either, if it's simple, it's going to be, it's actually going to be just a static value. Otherwise, if it's complex, it's going to point to some other locations. And you have a ref count. So in this case, ref count is basically how many references are there to that particular object. So in this case, there are 4, right? So there are 4 references. So that is how that is the basic meaning of ref count. When in Python, when the ref count becomes 0, that means that object is no more referenced. You're going to remove it out of memory. So basically, there are 2 kinds of garbage collection. Okay, we'll get to that point. So basically, that's a little bit funda about how garbage collection works on Python. It uses reference counting, right? And just to give you a little bit of understanding about how memory is managed, I kind of created this. Now, if you look at that, that is the function over there, you know. So the main is the first program that gets loaded, and when you do that, what it's going to be doing is, it has on the stack you'll have the main, just like in C. You have y and z over here. When you say y equal to 5, it basically creates an object 5 and points to that. When you say z is equal to some function, it basically pushes that function on top. The value that's passed to it will now point to 5. When you do some operation, it basically points to that. When you return it, this thing now basically points to that. That's just a very high level of how memory is managed in Python. Here's a little bit more complicated stuff. Let's say you have 3 functions, right? You have z is equal to f1, which basically will call that, and then x is equal to f2, which will basically call that. So there's 3 kind of functions. Now, in this, what happens is you have your main function, you have your variables, the objects, y is pointing to 5, you pass that 5 to this object, so y is pointing to that. X is now going to be calling another function. So, did I do something? Okay. Yeah, okay. So basically what happens is x is going to be called, and x, the value that you pass to it is going to point to that object, and then you create another object, right? Because x is equal to x plus 1, so you create another object. This x is pointing to that. When you return it, this gets that value, and when you return that, this is now pointing to that value. Is this making sense? Yeah? So now what happens to this? There are no more reference counts over here. So this can get deleted out from the memory. So this is just a very, I just put it there so that you understand how complex objects also
It's
work.
deleted in a sense, refreshes.
It is removed from the heap.
Removed it.
It is removed from the heap because no one is using it.
So does it look for the reference count in every cycle for what is there in the memory? So that
Every time, okay, so when does the reference count is stored as part of the object, right? Whenever you reassign, like whenever an assigning happens, like when you, in this case, when you said x equal to x plus 1, he will basically point to another object. At that point of time, he will decrease the reference count of that object.
at that point of time delete.
Yeah, at that point of time, please remove. When you this is just the way that complex objects work. Let's say you have a C which is pointing to a class. A class will have another variable which is pointing to another value. Just put it there just to kind of tell you how that memory looks. So yeah, so this is basically the answer to his question. When does reference count increase? When does reference count decrease? So when you're assigning a variable, say if x equal to 10, the reference count increases. If x was pointing to another variable, the reference count of that decreases. In the instances that we saw that, like, when a function is removed out from the stack, all the variables that will inside that is no more pointing to that. So the reference count of objects decrease every time that object namespace goes out of scope, when that name goes out of scope. There are another way that you can do is by using a function called as delete. Delete doesn't actually delete your object. Like, let's say you have a equal to 11 and you say delete a. It doesn't actually delete 11. What it does is it decreases the reference count of 11. If the reference count goes to 0, basically 11 is deleted. But if, let's say, a equal to 11, b equal to 11, and you delete a, you still get that object still is in memory, right? Okay, so we basically talked about garbage collection by reference count. And what is the benefit of using reference count? One, it's instant. The moment you initialize, or the moment a variable is not pointing to it, it's no more being used, he's taken out of memory. So it's instant, right? But there are issues with using garbage collection by reference count. I don't have animation for it, but let's say you have a linked list, right? A linked list, there is a head which points to one node, and that node is basically pointing to the second node, and the second node is pointing to the first node. Right now we have a circular kind of a reference. When does the reference count of this node become 0? Right? Even if you remove head, if you point head to some other node now, these two are no more being used. No one can access it because there's no one pointing to those two nodes. But those nodes will continue to exist because the node 1 is pointing to node 2 and node 2 is pointing to node 1. So the reference count is always 1, right? So it'll never go out of scope. And you might think this is rare, but it's not. Apparently this happens all the time in graph. Whenever you're using graphs like trees, or when you're using linked list or things like that, these kind of stuff happen a lot. So it is substantial enough that Python had to do something in order to remove it. Garbage collection by reference count doesn't really solve the problem, right? So we use something known as garbage collection by tracing. Now this is the basic method which is used by Java, which is used by C#. A lot of the compiled languages tend to use this kind of garbage collection. It just has there are different variants of garbage collection by tracing. So there are different kinds of tracing algorithms. The one that everything has these two stuffs. Basically, it's mark and sweep algorithm. The first mark part basically looks for all the active references, right? In the previous case, let's say head was pointing to a linked list, and then head points to another set of linked lists. So that first set of linked list that is not being pointed to, that is not being used by anybody, so it's not active. In the mark phase, So these two phases, right? The first phase is mark phase. So in the mark phase, he'll actually find all the active references. And the sweep is basically taking all the dead references and removing them off. Right, so there are different ways by which you can do it. I've seen some 3-4 variants of it. And these different variants are useful in different circumstances. What Python does is it uses a variant known as generational algorithm. So it's a tracing algorithm again. But what it does is, again, let me just go to that interpreter. So there is a library called as GC, right? We rarely use it. What you can do with GC is basically fine tune how garbage collection works. Now GC has something known as I forgot. Okay, it has something known as buckets or get thresholds. Okay. And what it does is it basically gives you 3 buckets, right? This is being used as part of that generational algorithm I talked about. So there are 3 buckets. What the garbage collection does is, in the first phase, so basically 700 is the frequency. So every time that every time you instantiate something, you will basically put it into this bucket, right? Every time you create an object, you will put it into that bucket. When it reaches 700, that is when he runs this script, which will basically do that tracing algorithm. Yes. And in that, one of the things that he does is, he will move whatever surviving objects that are there inside this bucket to bucket 2. Right? And this is the threshold of bucket 2. So in bucket 2, let's say if it goes beyond 10, he will basically move that to bucket 3. And bucket 3, if something is inside bucket 3, it will continue to exist, right? So bucket 3 means, it is going to exist till the end of that thing. It doesn't do. I'm not really sure why that 10 is there for. But yeah, so that is the basic way. Generational algorithms basically work that way. So you have 3 buckets, and the philosophy is objects which need to be disposed tend to die faster, right? Like let's say you create a function which has local objects. Those actually tend to go off from the memory faster, right? And so they tend to clean it up as fast as they can. So now what is the problem? What is the benefit of using a tracing algorithm? It tends to remove all the cyclical references, right? But what is the problem with the tracing algorithm? He runs in intervals. So let's say you have it runs. It doesn't immediately clean up your system. He actually has to wait up for that bucket to get filled, and then he cleans up your system, right? So there is a brief time in which your memory is not tidy. Now, when you couple both the garbage collection by reference counting and garbage collection by tracing, what happens is the garbage collection by reference count cleans up your memory fast, and the tracing algorithms will basically clean up your cyclical references. You have a lot of other stuffs over here. These are all basically used to control your garbage collection. You can disable garbage collection if you want to. You can enable it. Callbacks are basically every time a garbage collection calls, the P1 bucket, the bucket 0, you will get a callback every time you do that with the second. So basically you can get callbacks at every point of time. And you can get the count. Get count is basically what is the count of the. So currently it has 619 in the first bucket, 10 in the second, 0 in the third. Yeah, so basically that's all I have about garbage collection. There are a few more things that I thought you may be interested in. GIL I won't cover. Now the GIL is particularly important when it comes to garbage collection. And I don't know if the next topic is going to cover it, but you do not have a global interpreter log in Java, you only have it in C Python. And the reason is Java is pretty okay with handling multiple threads. C doesn't care, right? C expects the developer to take care of it. Now, what is the problem with having multiple threads when you're cleaning up garbage? The problem is one thread could be updating something. So one thread could be updating something while another thread is trying to access it. So if one guy says a equal to 11 and that the reference count of this object becomes 0 and it removes, gets removed out of memory, and the second thread has already assigned that value, so there can be complications. So this is the reason why we, one of the reasons, at least I think, why we have global interpreter lock. I don't know the other reasons. So one of the main reasons why we have a global interpreter lock is to stop different threads from accessing and corrupting the variables in memory. But Java, it does a good job with it. So Java, the JVM itself takes care of all the thread-related stuff. So that's Gil. Slots. Has anybody heard of slots? Okay. Yeah, it's not really used that much. I don't know why we would ever use it.
Descriptors?
Huh?
Descriptors? Lots?
No, the slots is basically a way by which you can prevent a class from having many variables. Like, let's say you can basically define slots so that a class can have only A and B, right? If you want to create another method or something, it will give you an error. So slots is basically used for memory management, right? It prevents the underscore dict, the dunder script dict that you have with every class. Basically, it doesn't make sense with slots because he's not going to keep track of that. He will have something known as slots, and slots will be the only thing. Only the methods which are defined in the slots will be the ones that you can access. So it's kind of memory management kind of a thing, and slots tend to live in memory for far longer than the others. Huh?
It will increase the efficiency also.
It will. So yeah, it may increase the efficiency. Depends on how you use it.
What's the purpose of it?
Memory. It's all about memory. It's about how if you're creating something where you want the memory to be absolute, that's when you use slots. And the deleter is basically the destructor magic method. Yeah, it's basically the destructor. So this is different from the delete built-in function. So the difference is in delete, that object actually gets removed, whereas the delete actually just decreases the reference count. I'll take questions. Anybody can see. So if you have say, I think there is a referrer count, get referrers of say referrers. I think there's a get referrers.
Double F.
Singular,
Oh, okay,
double
okay, yeah. Okay. And you basically get the different objects that you have. It doesn't take no questions? Yeah.
So like when we assign a variable, any object to a variable, you said that it first looked that it is in the memory heap or not. So is there any table or mapping kind of thing that where it starts looking whether the object is in the memory or not?
No,
Like,
so basically on the stack when you say you have A, for example, in this case, it will have the location to where on the memory it should access. So that value is stored over there. So there's no table as such.
So now when I again assign B equals to 100, so it will point to that particular location only directly because
Right.
so there has to be some mapping that
Okay, yeah, there is a mapping. So for garbage collection to also access that, there should be a mapping for all the objects that are in the heap. So there is a kind of a mapping that exists for all the objects that exist on the heap. Yes.
So it is accessed via some table or something, like how it is?
I don't know. So this get referrals basically talk about all the, you can see that 101, 100, 100, 100 is there. So he's basically referencing a table. He's taking it from a table, but I'm not sure where he's picking it up from. But it is, yeah, you're right, it exists.
Just a stupid question. What is none? Is there any memory allocation for none?
Apparently, yeah. I think so. I'm not sure, but none is, none is,
Idea of none.
huh?
Idea of none will have some location.
Okay, as an object,
Everything is an object.
Yes, yes, yes.
Everything will have an
no, there is, okay, there is some object called as none.
Yeah, because
Exactly.
is a
Yeah.
none type of.
I mean,
Yeah, the type of
fundamentally in the
non-type.
Python, everything is an object. All objects are like.
Exactly, yeah.
There is something like just one byte which is stored.
Maybe, yeah. It might just be, yeah, it might be just one byte or something. But yeah, there is, I don't know, there is another time. Yeah.
How is the tooling for production GC tuning?
I'm sorry?
How is the tooling for production GC tuning for Python? I did not observe, usually had a good JVM GC monitoring for Java.
Okay.
But for Python it is very minimal, like there was not much insights about what kind of GC is happening and how much CPU is spent on GC. So those would be
There
some,
are tools for that. I have not used any, but I have actually seen a few blogs mentioning how much of memory is being used and how much of. So there are some tools, but yeah, I am not aware of what those tools are. Yeah.
So I have heard that PyPy also does some memory, good memory management. So how GC works differently in PyPy or is it from same?
So PyPy is basically an implementation of Python in Python, right? I don't know how they handle garbage collection. I'm not sure.
When you talk about Python running JV, how is it garbage collection done by the?
So the garbage collection is different. It still uses reference counts. I mean, it uses reference counts. Now I think even in JVM, we still do the tracing algorithms. We still have. I'm not sure if we use the same variant of as we use in the C Python, but we do use some kind of tracing algorithms to remove these cyclical references. But we also leverage JVM for the cleanup. So I'm not sure if that tracing algorithm, what we do is we call the basic underlying Java, or they have a different implementation of it. But yeah, we use both of them again, but I don't know who's doing the, it should be the underlying Java who's actually taking care of cleaning up. So he must be just calling that and then this guy cleans up something.
So one usually whatever there is not the reference count, right? For example, if I want to find a reference count.
Yeah, it isn't. It is not. I was hoping it would be, but yeah, no, it is not. There's one more stuff that is here. It's called get reference. And it always gives me empty.
Try for 100.
Values.
Values.
100.
Referrals.
Yeah, it always gives me empty.
Referrals of
Huh?
Reference get it count.
Sister?
Get reference count. REF.
Probably try get referrals of 100. When you did get referrals, instead of A, you could probably try 100.
Reference of 100, you say, right?
Double
No,
Double R, right?
no, double R. This way.
First level, not the last.
REFE double R, yeah.
No, this is basically, yeah, so I think the first two variables, are they referring 100? Yeah, I think it is. Yeah, might be, not sure.
What is something called get count?
The get count doesn't actually take any, it's basically just a
How many objects
There's
are
no
there?
overloaded. There's no overloaded form of that. That it's
I don't know. I mean, this is all that I could find in GC. But yeah, someone was selling sys dot something.
Get ref count.
Sys dot get
Ref. No, no. All is one. All one. No underscores.
ref count, is it?
Yeah.
There you go. Okay.
But even when I initialize a new entity,
What's that?
when we initialize a new entity also, the ref count goes to the queue. Why is it?
So because
Should be one, right?
yeah, might be, but then yeah, I noticed that you have a lot of stuff over here. Let's say you have 100, 100, you have 100, none. So this 100, none, I'm not sure. So it must be, no, I don't know. But there is a 100, none, which I don't understand. So it could be because of that. Yeah.
I would just like you to try something. So you could just initialize A to 257
Okay.
and yeah, and B to 257. Yeah, check the IDs for both.
The ID for both. is it?
Yeah, ID of A.
Oh, interesting.
This is called string intern.
Because after doing it, it will
So it stores 0 to 255
As a
memory,
null.
and those all
different
are
kind of objects.
yeah. After 255, I mean after 256 basically, whatever values you create, they are created newly. They are not referenced to the same thing. So even if you create something with 257, I mean multiple 257s, they are going to be created separate spaces.
I think they become objects of it.
Because you frequently use 0 to 2. So they are
Oh, the
always
different count will
no
work now.
matter how many times they are
Yeah.
Now the different count may not work the way that we expect because now there are different objects all together at the same.
Yeah, yeah. So there'll be two objects which have the value 257. Is it?
yeah, two values with 257.
And that is because anything
Based on what I've read is that 0 to 256 is what you frequently use, or I might be wrong if someone else knows something else.
Okay.
I faced a scenario when let's say I have put in a data like this, two variables, let's say 3000.
Okay.
If I do an ID of 3000, again the ID of 3000, it will be same. The third time when I do an ID of 3000, it gives me a different value.
Is it?
I have seen such kind of things.
Maybe this is a fodder for another talk.
Actually, I found this from I think Raymond Hettinger's tweet. So algorithm he frequently tweets.
Yeah. So I mean, I have very minimal knowledge about these stuff. So yeah, I have no clue why that would happen. So, but yeah, it's a good insight though.
You mentioned about the three algorithms of mark and sweep.
Yeah.
Can you name this?
I don't know. So there was this blog where this guy was talking about I can probably add it in the comment section like once we're out, but I can show it to you. What he does is he basically used a dumb mark and sweep algorithm, and then he used another variant which is a little bit more optimized. So there are three algorithms, and he said one basically cleans up stuff faster, one cleans up stuff faster, but it kinds of moves. So if you have a memory and you've allocated a bunch of stuff here, he will clean it up, but the memory keeps moving, right? And there's one which doesn't do that. He will do the compaction as well. So there are different variants of that mark and sweep algorithm. I can probably put it in the comment section.
Okay, we are running out of time. If there are any questions, you can take it offline. Okay, thank you for Rivas for teaching how